Morning, everyone. How are you feeling this morning? Good, good. I just want to start off with actually an apology because I really missed something out last night in the astronomy because when I do these astronomy shows, I like to talk about, take you on this journey to show you how big the universe is. And part of that is to try and intimidate you a little bit. To make us feel small, because we are small, we're very small. But I like to finish that off with saying we may be small, but we are not insignificant. And it's just such a lovely thing to be able to share the night skies with people and to bring that home, because the fact is the creator and sustainer of the universe, whoops, this is ticking forward, loves us and gave his life for us. So it puts a completely different perspective on our place in the universe, doesn't it? The creator and sustainer of this loves me. And as Juliet said, knows the number of hairs on our head. It puts it all into perspective. And I find it just, instead of creating a feeling of insignificance, it does the exact opposite. It creates a massive feeling of significance. So just wanted to put that up again. Okay, thank you so much. So we're going to deal with this question of ages. It's sort of been buzzing around in what we've talked about. And really, we should bear in mind that this is a mechanism question, not a meaning question. This is not a matter on which our faith depends. But in addition, you can almost say it's also a minor, not a major. So I like to have those distinctions. The age of the earth is not important to our faith. The age of the universe is not important to our faith. But it is kind of, I'm sorry, I've got that. We've already done that. It is interesting, isn't it? It's fun to study it. So that's why we're talking about this, I feel, is maybe to clear up some confusion, but also I believe, and I'm sure Dennis would say, and I'm sure Professor Block would say, it's so wonderful to study the work of the Creator. And that's what motivated, of course, the first scientists. Okay, but in this, we've also touched upon this as we've gone along. David's introduced a quote that I'm going to reintroduce. We must be careful, because if we make silly claims, we can damage not only our credibility. You're welcome to damage your own credibility. Please don't damage the credibility of the gospel. You know what I mean? If, as a Christian, as a pastor, we say stupid things, then that doesn't just bring us into disgrace, it can bring the gospel into disgrace. And David gave this quote that I'm just going to reproduce here. We're obviously on the same page. Now, it is a disgraceful and dangerous thing for a non-Christian to hear a Christian, presumably giving the meaning of Holy Scripture, talking nonsense about these topics, he means science, and we should take all means to prevent such an embarrassing situation in which people show up vast ignorance in a Christian and laugh it to scorn. The shame is not so much that an ignorant individual is derided, but that people outside the household of faith think our sacred writers held such opinions, and to the great loss of those for whose salvation we toil, the writers of Scripture are criticised and rejected as unlearned men. If they find a Christian mistaken in a field which they themselves know well, and hear him maintaining his foolish opinions about our books, how are they going to believe those books in matters concerning the resurrection of dead, the hope of eternal life, and the kingdom of heaven, when they think their pages are full of falsehoods on facts which they themselves have learnt from experience and the light of reason? And that's St. Augustine from the 4th and 5th century. So it's not a new problem, guys. As Christians, we have a problem with mouthing off about stuff we don't really understand. And I'm afraid in the area of science, we're particularly bad in doing that. So let me just give you an example about making silly claims. I'm sure some of you have heard these. So what about these silly claims about the Bible? Have you heard someone mentioning something along those lines? The Bible, probably 2nd, 3rd century, long after Christ, nobody knew anything. It was all cobbled together, complete rubbish. Now, anyone who knows anything about the history of the gospel and the manuscripts we have, know this is gibberish. So when a non-Christian, when an atheist wants to use this as an argument to not believe the Bible, what do we feel? We feel, you don't know what you're talking about. All it does is diminishes their credibility. What about this one? The Bible is unreliable, we don't have the original manuscripts, and it's impossible to work back from what we have to determine anything with any degree of confidence. Again, I'm sure there's many people John could, I'm sure, share on this. It's not true. Textual criticism is a well-developed science, and we can work back from the copies we have and the copies of copies, we can work back to get a really good idea of what the autograph actually said. This is I just threw this one in because I was listening recently to an atheist give an explanation for why the resurrection never occurs. Now, I'm hoping Kanu is going to come and give an explanation for why the resurrection did occur. But his explanation was, no, Jesus didn't rise from the dead. What happened is, after running away terrified from just the temple guards, the disciples got it together and they decided to overpower the century of Roman soldiers who were crucifying Jesus with a whole legion just a stone's throw away. They did that, managed to take him down from the cross and presented him as a resurrected person to everyone. You know, and that doesn't make sense on so many levels. So what do we feel when someone says that? It just diminishes their credibility and the credibility of atheism, basically, if they say stupid things like that. But we can also, as Christians, we can make stupid claims. What about this one? Is this one you've heard before? The Earth's magnetic field is decreasing, and if you look at the rate it's decreasing and the maximum value it could have had, that proves the Earth has to be very young. Has anyone ever heard that one? Oh, I'm glad. I'm delighted. Because this regularly appears. Does anyone know why it's wrong?
It's a cycle?
It's a cycle. The Earth's magnetic field does not linearly decrease. It actually has had something like 200 complete reversals. So you cannot work out the age of the Earth from that. Okay, what about this one? The carbon dating scientists use to determine the age of the Earth is unreliable. Has anyone heard that one?
Yeah.
Okay. What's wrong with that one? Yeah, scientists don't use carbon dating to determine the age of the Earth. You use it to determine the age of organic material. The half-life of carbon is 5,500 years. It's not going to be useful for determining the age of the Earth. What about this one? Have you ever heard that one? Radioactive decay rates are affected by rock being underwater, so radiometric dating is unreliable. Anyone heard that one? Yeah? Radioactive decay rates are not affected by being underwater or pretty much anything you can do to radioactive isotopes. Here's the last one you can maybe think about. Applying potassium-argon dating to newly formed volcanic rock gives ages of millions of years, proving this dating technique is unreliable. I'm not going to deal with that one, but we can discuss that later if you want to. The whole point is, unfortunately, people speaking in the name of the church constantly make ridiculous claims, and the only effect of that can be negative for the gospel. You know, it creates the impression that Christians are not honest conveyors of truth. They're not sensible, they're not honest, they're not reliable witnesses to anything, and that's a problem. So, summarize this issue of ages. It's a minor, not a major. We really should avoid making silly claims, but it's still a fun mechanism question, so that's why we're going to dig into it. Okay, so we're going to start off with the age of the universe, very, very briefly. I'm sure many of you are familiar with some of this. This guy called Erwin Hubble, after whom the Hubble Space Telescope was named. 1929, he was doing some studies on these nebulae which were out there, and people didn't really know what they were. Some people thought they might be other galaxies, some people weren't sure. Here's one. Anyone know which one this is? Andromeda, excellent. M31, this is Andromeda. This is our closest big galaxy. And what he noticed was the light from faraway stars was redshifted as they were increasingly far away. So what redshifted means is basically elements have a spectroscopic signature represented here by these dark lines, and that always occurs in the same sort of wavelength. It's like a fingerprint of that element. So if it gets redshifted, the only thing this can mean is somehow the light is being effectively stretched out. Now that can be because they're running away from us or because the fabric of space itself is being stretched. But he noticed this redshift that was bigger and bigger as objects were further and further away. And he was able to measure the distance these objects using a technique, various techniques, but one of them is what they call a standard candle technique. So if you imagine a whole series of candles separated out in space, they would have trouble burning, but don't worry about that for a second. If you were able to study the brightness of an individual candle, you could actually work out how far it was away by its relative brightness. So you know as it gets twice as far away, it gets 4 times as dim. 4 times as far away, 16 times as dim. So by measuring the light of the brightness of your standard candle, you can work out how far it is away. Now, we have, fortunately today, amazing set of standard candles called Type 1a supernovae. These are not core collapse supernovae. They're a really cool type of supernova that for some reason, well, not for some reason, for some lovely physics reasons, when they explode, they basically all explode with the same brightness, which is really, really useful. And they're also really, really bright. So you can see them a long way away. And when you spot one in a galaxy like this one here, you can basically work out the distance to the galaxy. So that has been done. And this extraordinary thing is discovered, that if you look at the distance, if you plot the recession velocity, the apparent recession velocity, that redshift thing, of galaxies against their distance, you get this straight line. And this has really held up after the work of Owen Hubble for stuff right into the present day. What is going on? Well, here's a simple two-dimensional analogy for what's going on. So I'm sort of reducing the universe to 2 dimensions here because it's a bit easier to contemplate then. Imagine everything in the universe was on the surface of a balloon, okay? Balloon-like structure. So here you've got your galaxies stuck on your balloon, and then imagine pumping the balloon up so it stretches, it expands. What you will see, let's imagine you are this galaxy here. As the balloon expands, every galaxy will move away from you. And the further away the galaxy is, the faster it will seem to move away from you because there's more balloon fabric between you and it. Okay? And every single galaxy will see the same thing. They will all observe every other galaxy running away from them. And in terms of the surface of the balloon, there isn't really... Chuck's got a...
Doesn't that presume that we're in the middle?
No, because basically every single galaxy will see every other galaxy rushing away from us because the fabric of the balloon is stretching. So in terms of the surface of the balloon, there is no middle. And this is true with the Big Bang. The Big Bang was actually a sort of a derisory term devised by Fred Hoyle, who hated the Big Bang model. And it was like, oh, it's like a Big Bang, is it? And it's a really bad name. It should better be called the Big Stretch. Because Big Bang implies explosion, implies it was one place that was the center of it all. That's not the case with the Big Stretch, as it should be. Okay, so if the universe is... Sorry? Cool. If the universe is expanding, you can kind of like rewind the tape using the wonders of the general theory of relativity, and you can find out how old the universe is, and the answer is 13.8 billion years. So, and that's all part of a massive evidence we've got for the Big Bang that I won't go into the totality of it, but I'll just flick up a few bits. Have some of you seen pictures like this? The cosmic microwave background radiation. This was a really fantastic discovery, something that sort of is a fundamental prediction of the Big Bang. The idea is, as the universe expands, early on it's so hot that the universe is not made of gas, it's made of a plasma. A plasma is when all the electrons have jumped off the atoms because it's so hot. And then you've got these positively charged atoms and these electrons. It makes this very electrically charged sea, and light cannot propagate through that. So the universe is opaque. But as the universe expands, it cools. And so a time arises, it's not a single time, but it happens gradually when the electrons hop back onto the atoms because it's cool enough, and suddenly the light can propagate. So suddenly you get this light spreading throughout the whole universe. And it starts off as visible light, but then as the universe expands, it gets stretched by a factor of about 1,100, and it ends up in the microwave region. And this light is everywhere. So wherever you look, every part of the universe is shining this light towards you. And this was what was discovered. Penzias and someone or other, I think that's what he got the Nobel Prize for. Everywhere you look, there's this microwave background radiation, and it's got exactly the form that you would expect from the Big Bang model. And you can derive all sorts of fascinating things about the conditions in the early universe, because this was basically emitted about 380,000 years, very, very early after the Big Bang. And there's also lots of other stuff, baryonic acoustic oscillations. These are shapes in the distribution of matter in the universe to do with early sound waves propagating through the very early universe. and look, you've got the data and you've got the predictions of the Big Bang model. Is basically exactly matches what we see.
But how is the microwave background detected? That wasn't sure.
So first of all, someone started with a big microwave horn somewhere in the States, wasn't it? And they were trying to do something else, and they kept on getting this weird noise. And they thought at one stage it was some pigeons that had pooped on the instrument, cleaned it, and still there. And then they just noticed wherever you point, you've got this microwave background. And then people started thinking, wow, this might be a relic of the Big Bang. They started putting satellites into space because that made it much easier because less noise. And you got things like WMAP, and then finally Planck. And there's even more studies this year. There's going to be some amazing studies on the microwave background radiation that are going to be released. And basically, yeah, it was there exactly as you would expect from the big stretch. And also the relative abundance of elements in the universe, that drops out straight out of the Big Bang model. Basically, as the universe expands, everything's too hot to even make nuclei initially, and then you come through a phase where it cools enough that you can have hydrogen, and some of the hydrogen can stick together to make helium, but then it cools so that even that process doesn't happen. So there's a little window for making helium, and some of these other helium-3, helium-4, deuterium, and maybe a bit of lithium. And if you look at the abundance of all of them, except for the lithium, which is a little bit out, but that's an interesting area of research, it exactly matches the predictions of what you'd expect from the Big Bang. So the evidence of the Big Bang is really, really overwhelming. Okay, so let's go with that. And the key thing, of course, is none of this in any way contradicts the idea of a creator. This is how he did it, and it's really cool. So we can study this with joy and without any sense of, ooh, it wasn't God, it was a Big Bang. You know, I don't know why a lot of people don't like the idea of the Big Bang. If you have something not to like, it should be the steady state theory which preceded it. Because the steady state theory said the universe has just always been there, eternal universe, nothing really changes, doesn't have to be started or created in any way. Turns out it's wrong. It was created at a specific point in time. Okay, so that's the universe. Where do we fit in? This is a very brief picture of the entire history of the universe. Basically going from left to right, Big Bang, expansion, terribly hot stuff, structures start forming, galaxies start forming, and then sort of somewhere over here, stars start forming, planets start forming, and we get our Earth. And we think that process happens something like this. Basically, when gravity gets to work, it produces disks. And that's because it's much easier to squash a rotating body of gas, and everything's always rotating about some axis. It's much easier to squash it along the rotating axis than pull in the outside rotating stuff. You see that with those ice skaters. You know when the ice skaters do that thing and they pull their arms in and speed up? It's all to do with conservation of angular momentum. If you talk to the skaters, they'll tell you there's a force that resists them pulling in their arms. So the same thing happens on galaxy scales, on solar system scales. It's much easier to squash it like that than pull it in against the spin, basically, of its rotation. So we thought something like this would have happened. Massive hydrogen gas, helium, enriched with some heavier elements. Interesting story there. We'll go, maybe I can tell you a bit about that later. But it's all there, and most of it ends up as a star in the middle. Gravity pulls that in. Big hot blob of plasma. Nuclear fusion kicks off. Bang, you've got a star. But there's stuff left over in the outside swirling around this star, and some of that starts to accrete. Gravity pulls stuff together, and once you've got a lump, that will tend to put more in and make a bigger lump and a bigger lump. And what you can see here is some of these lumps. I don't know if you can see that little white lump there, white lump here. There's another lump somewhere over here. And the sunlight is being blocked by the lump. That's why you've got that black thing streaking out behind that tail. And what you can see is where you're getting a lump, read planet, as it goes round, it will hoover up all the grot in its orbit. So you'd expect to see basically a pattern like this with these dark rings where the planets are forming and sucking up lots of gunk. And lo and behold, this is an image from the Atacama Large Millimetric Array, exactly what we expected happening. You've got your star in the center. These dark rings are where planets are forming and sucking in the gunk. Okay, and so God made our solar system. Again, for the risk of being boring, this is just the how. It's not the who and the why. This is how God did it, and it's beautiful. It's beautiful. So we got a solar system. Okay, that's a bit astronomical. Can we get down to Earth now? What about the age of the Earth? there's a lot of evidence that the Earth is very old. Okay, we can start with some really simple evidence, which I think we're all familiar with, tree rings. I think we've all spent a few hours probably trying to count backwards to work out how old a tree is, and it's a really effective way of working out the age of a tree. Do you know the story about the oldest tree in the world? So that there was, California has the tallest trees in the world, the most massive trees in the world, and the oldest trees in the world, the bristlecone pines. It's on my bucket list one day to go and see all three if I can. Anyway, so that this American government institution were actually studying these really old bristlecone pines, and they had this coring thing, because you sort of take out a core and then you count the rings. And with the bristlecone pine, it grows so slowly, you have to use a microscope to count the rings. It's incredible. Yeah, very, very slow growing. And they were doing this, and they were finding these amazingly old trees, and they put this core into this one tree, and it got stuck. So they phoned home, and they said, look, our core is stuck. And the guy said, well, cut the tree down and get the core out, of course. So they cut the tree down, and afterwards they realized they'd just cut down the oldest tree in the world.
Oh.
And they've never found one older than that. Anyway, but you can count back your tree rings like that. And then you can do something really clever, because you can see the growth rings are the light bits. That's what happens during the summer when the tree grows. And there's kind of a pattern. You've got a really good year here. You've got a big growth ring. That was a bad year. The growth ring was quite small. So you actually get a pattern of growth rings that will be shared by all the trees in an area. So you can actually put them together. You can take one piece of wood and you can match up the sort of patterns with an older piece of wood, and then match that up with an older piece of wood. So you can kind of build up a dendrochronological record going back much longer than the oldest tree we have. And doing that, you can easily get back to 10, 12, even 15,000 years. You can count back the individual rings. Okay, but we can do more with ring counting. I don't know if you've ever heard of varves. Varves are also annual layers, but this time deposited at the bottom of a lake. So you'll find that because the conditions vary between summer and winter, you'll get these different coloured layers. That's the winter one, this is the summer one, winter one, summer one. And you can see them building up in real time at the bottom of lakes. And again, you can count them back. So through the process of sedimentation, we've studied these for a long, long time, and we can actually see them obviously being laid down now as well. And things like pollen, of course, show you this was the summer layer and this was the winter layer. So there's really very little doubt about their nature, though sadly, some people want to try and cast aspersions on this, which, as I mentioned earlier, really just brings them themselves into disrepute. And they can be turned into rock, because of course rock is really things like these layers. Heat and pressure, you squash it, you can get rock, and that indeed has happened. And just as a final point, the Milankovitch cycles, I'm sure you all think about the Milankovitch cycles a lot. Basically, there are cycles in the solar system where things change over time. So the obliquity of the Earth, that's the angle that the Earth tilts at in relation to the plane of the solar system, it actually changes over time. It kind of wobbles like this, very slowly. It's a 40,000 year wobbling cycle. And as you'll see, you can pick up these wobbling cycles, changes in these varves, again, showing clearly their annual layers. And they can get fossilized. Heat and pressure can turn these muddy layers into rock. Here's a good example of that, the Green River Shale. Very huge deposit. It actually extends over 3 states in the United States. Massive and really interesting. Lots of study have been done on it, because of course this is the kind of structure that you frack to get oil and gas out of. So enormous amounts of oil locked up in these systems. And it's really, really, really been squashed. So these layers are tiny. The average var thickness is about just under 0.2 of a millimeter. So again, you have to use a microscope. You can kind of see that there. That's a centimeter. So you're well, maybe that's even a millimeter. I don't know, but they're really, really small. You have to use a microscope to study them. So they're absolutely tiny, fraction of a millimeter, and this is what the formation looks like. These are cattle or horses down the bottom here. This thing is over 1 kilometer thick. It's absolutely massive. 15 million annual, well, sets of 2. So if you divide that by 2, you're getting over 7 million years of deposits there. Very, very old.
Why divided by
Sorry, because there's 2 layers. Sorry, the 2 layers for each year.
Oh, okay.
Yeah. So, and there's lots of other things we can look at. Ice cores, we can look at all sorts of things, but I think you get the point. But if we want to move on from that, we know it's old, but how old? So there's 2 slightly different questions we can ask. How old is our solar system? How old is the Earth? And they're not quite the same, because if you remember this picture, when the solar system formed, layers like this, like this asteroid belt between Mars and Jupiter here, basically once that formed, it's pretty much stayed the same. You know? So you've got really pristine rock from the formation of the solar system there. The Earth, not so much. The Earth is constantly in motion. You've got these processes, subduction, the Earth's crust, so rock that's been formed is being sucked under, melted, spewed out again in volcanoes or at the mid-Atlantic, mid-oceanic ridges here. So the Earth, very ecologically conscious, it recycles and consequently destroys a lot of the oldest rock. So we're not going to find rock, or it's very difficult to find rock that even gets close to the original age of the Earth, but that's okay. Okay, so how are we going to study this? We're going to use radiometric dating. So again, a lot of rubbish gets spoken about this, so I just want to dig into it a little bit to try and explain why scientists like radiometric dating, what you can do with it, and what the results are. So it's based on the idea that some isotopes of elements are unstable. Here we've got uranium-238. I think we're also all familiar with uranium-235. That is the isotope that you make nuclear bombs out of. So it turns out that is even more unstable than 238. It's constantly emitting these slow neutrons. And so if you put enough of it together, the slow neutrons, enough of them will hit other uraniums, cause them to fission, and the neutrons from that creates neutrons, etc. You get a runaway chain reaction, you get a nuclear explosion. But there's other isotopes of uranium. 238 also decays. It doesn't spit out neutrons so much. Oh, sorry, that was the wrong thing. It spits out a helium nucleus, also called an alpha particle. And when it does that, you can see it emits, the red ones are protons, the blue ones are neutrons. It loses 2 protons and therefore becomes a completely new chemical element. It becomes thorium. And this is called the parent nucleus, or the P, and this is the daughter nucleus. Does that all kind of make sense? Cool. Okay, one way you can envisage this is a little bit like an hourglass. You can conceive of the parent being the sand in the top of your hourglass, and every time a decay takes place, it's like a sand grain drops through to the bottom and creates an extra daughter nucleus. So you can imagine, you could see already, you could use this as a timing mechanism in the way we use hourglasses as time. If we know it's full up with sand at the top and we come back and we see it's now half full and we know how quickly it empties, we can work out how long it's been emptying for. And before we get into the details of that, I just want to flag up an interesting point that really gives us a pointer about age: empty hourglasses. So we know the half-lives of many, many radioactive nuclei, and there's many of them, okay? What we notice is lots of them are not present on Earth. But often we can see their decay products. We can see what they have decayed into. So for example, plutonium. If we want to make plutonium, again to make another nuclear bomb, we have to make it because there's none on Earth. And that's because its half-life is quite short, only 24,000 years. But what we notice is if you look at the half-life of what we've got, we basically don't have anything in the Earth that isn't constantly being created by a radioactive chain, decay chain. We don't have anything that's like younger than about 1 billion years. So straight away that's giving us a clue. The Earth is probably even older than 1 billion years because they've had time for all those nuclei to decay away. Just an interesting thought. Okay, so why are we confident about using this dating? It really is extremely well understood. And thousands of dedicated scientists, people like Dennis, people like Bob White, I don't think he really focused on this, but he did geophysics. There's lots of dedicated people have spent their lives with using it, and it's really been perfected, I guess one could say. And there are lots and lots and lots of different isotopes that you can use, which we'll see is very helpful. We know the decay rates, they've been measured very accurately. The error is really less than 1%, it's really tiny. Not affected by the environment because you've got the nuclei which are right at the center of the atom. It's not affected by things like pressure. Unless you're talking about tiny nuclei like lithium, unless you're talking about insane pressures like putting them in a diamond anvil, you can see slight tweaks to the decay rate, but that's completely irrelevant to what scientists do with radiometric dating. And also, these decay rates depend on fundamental constants of the universe. So we kind of know they haven't changed because we can actually measure the past history of the fundamental constants of the universe. You remember that spectroscopic fingerprint of the elements that we looked at with the redshift? The shape of that depends incredibly exquisitely on these fundamental constants of the universe. And so when we look at light that's come from a very, very distant galaxy, we can check to see whether the fundamental constants of the universe have changed, and they haven't. So there's many reasons to think that this is a really, really good dating technique. But there are challenges. And sadly, again, you can see it kind of bugs me quite a lot. Some Christians focus on these challenges in a not very honest and faithful way, and they'll present challenges as if they haven't been resolved, when in actual fact there are answers to these challenges, and it would be much more honest to present the answers along with the challenges. Anyway, so what are the challenges? I'm sure you're all thinking, but Phil, we don't really know. When we come to our hourglass, we don't know how it was set up. Maybe it was full at the top and empty at the bottom, and maybe it was half and half. So we come along and we look at what's happened to the hourglass. How do we know the initial conditions? How do we know how much P and D was in the hourglass to start off with? Very good point. We'll come to that. And what if, the hourglass is not particularly solid? What if sand can actually leak out or can leak in? And this is certainly the case with radioactive isotopes in rocks. If they get hot enough, the elements, the constituents of the rock can become mobile. So you can get stuff moving in and out of the rock. Potential major problem. But there are a number of dating techniques. I want to talk about one in particular that address these issues beautifully. So one is called isochron dating, and that's what I'm going to talk about. Another is called argon-argon dating, which is also amazing, but I'm not going to talk about that. Okay, so how does that work? Both deal with the issue of not knowing the initial amount of parent and daughter. Now you think, that's impossible. No, it's not. It's actually possible. And both have what I call inherent self-checking mechanisms. And this is really, really important. They have built into them a way of checking to see whether the system has behaved as you want it to behave, to check whether everything is in order. So let me give you an example of inherent self-checking mechanisms. I used to work in a spectroscopy lab, and we used to have very delicate optical instruments delivered, and sometimes the people who were delivering them were less than careful in the delivering process. And they'd arrive and you'd unpack it and this thing was smashed. And you'd say to the people, did you drop this? Like, no, Governor, no, definitely not, no. And so what we had fitted to them, after a while, it was actually the company selling us, was these inherent self-checking mechanisms. So, and you can see two of them there. You've got this tilt watch and this shock watch. And they're really, really clever. So with a tilt watch, because you often don't want to tip things. You don't want to tip things, you don't want to drop things. Can you see you've got this set of sort of paths where little balls can be held. And basically, as you tilt it, a little ball can come out of where it normally sits. And if you tilt it so far, it will drop into one of these, and you cannot get it back. So, and then if it goes further, it will drop into the next one. So in actual fact, it creates a record of what it's been subjected to in terms of tilt. And you can see that. So the people will come along and deliver it, and you would know what's happened to it. And then over here, I've got a shock watch. Basically, you design this thing so if it experiences a shock, something breaks, and these tiny little balls spread out into the whole thing, and you can't get them back in. And that carries evidence that someone dropped it. And so literally, after we had these installed, you'd open up your instrument and it would be smashed or something, and you'd go to the guys, you didn't drop this. No. Well, actually, this shows us that you did drop it. And, oh, well, there was that one time. Yeah. So basically, it's an inherent self-checking mechanism. Does that kind of make sense? You've got the same thing with isochron dating. So, isochron dating. This looks quite a complicated plot, and I guess it is. But basically, this is rocks from the moon, incidentally. What you do is you use a very clever method of measuring the parent and the daughter, but you also measure another isotope. This is of neodymium, another isotope that's the same chemical element as the daughter, but it's not radioactive. And the cool thing is, when the rocks formed, neodymium, the chemical processes don't care about which isotope it is. Chemical processes cannot signal out a particular isotope. This is actually why purifying uranium-235, getting rid of the 238 and just taking out the bit you want to make a nuclear bomb with, is actually so difficult because there's no chemical way of telling apart uranium-238 and a 235. So you have to use a centrifuge to spin out the 238 and gradually concentrate the 235. And this is why rogue states like Iran, it takes a long, long time to get enough enriched 235. So chemically, they're identical. So when the element is made, the ratio of 143 to 144 basically will be the same right the way throughout all the materials that get made. Okay, and often you'll find a rock will contain different types of minerals. And they will contain different amounts of samarium, which is, sorry, didn't mean to do that, samarium and neodymium. And what that enables you to do is create one of these plots. Each of these points is basically a different mineral in your rock deposit that was made at the same time. And using this clever ratioing process, it turns out it doesn't matter what the individual parent and daughter was for each individual sample. It simply doesn't matter in the measurement. What matters is the slope of this line that you create. That's what gives you the age. And so you get this, in this case, you've got a beautiful straight line. What does that tell you? It tells you the technique has worked. If the isochron dating didn't work, if it wasn't valid, you'd just get a splattering of points. And sometimes you do. If you get a rock that hasn't sort of experienced a uniform history, you won't get anything like the straight line. So the straight line in itself is an inherent self-checking mechanism that what's happened, what you think has happened, really has happened, and this technique is working. But there's more. There's more. So there's two different classes of rocks were taken here, these mafics and these plagioclases, and mafics are a stronger type of rock. So you have to heat them more before the chemical elements in them become mobile. And what you can see is the mafics are lying beautifully on this straight line. And that tells you that none of the parent and daughter has moved during the time that rock has been sitting there on the moon. But if you look at the plagioclases have what they call a lower closure temperature. So you don't have to heat them as much for the elements within them to become mobile. And can you see there's a little bit of noise on it? So this is so cool. It not only tells you the age of the rock, it actually tells you something about its heating history during the time it was sitting on the moon. It was heated enough to get the plagioclase elements to start to move, but not hot enough to get the mafics to move. And you can extract an age. It turns out the moon is about 4.456 billion years old, which very much fits in with our models of the formation of the moon. Does that kind of make sense? I don't expect you to fully grasp isochron dating straight off because it is quite complicated, but does that sort of make sense? Yeah. Good. Okay. Okay. So, of course, nothing is 100% reliable. Nothing in life is. But we've got these inherent self-checking mechanisms, which really, really helps and gives you great confidence that the technique has worked. And we use multiple independent techniques, multiple isotopic systems. Here's an example. So we've got a rock from Greenland, pretty old rock, and we've used a system of parents being uranium, daughters being lead, a radioactive isotope of lead turning into another one of lead, a non-radioactive isotope of lead, rubidium, strontium, lutetium, hafnium, and samarium neodymium, which is a very favorite one. And look at that. You can see all the ages are adding up. Now, there's really no way to explain that except that the technique is really, really working and it produces a valid age. Within the error bars, of course, each technique has a different range of error bars inherent to it, but you can see you're getting an age of about 3.6 billion years consistently out of that. Even more amazing in some ways is if you look at a radioisotopic dating done on meteorites. So here, you have incredibly large numbers of samples, and again, you're using very different techniques: samarium, neodymium, rubidium, strontium. Down here again, lutetium, hafnium, osmium, and I'm not even sure what Re is, but there we go. Lots and lots of different rhenium, lots and lots of different dating systems, and lots of different samples. 50 samples here, 38 samples there. And look at the ages. Within the error bars, again, they're coming in really, really consistent. And it's coming in somewhere around 4.5 billion years. And these, remember, this is the formation of the solar system. So, because these basically will have sat there since the formation of the solar system. Okay, so what's the answer? The answer is solar system's about 4.5 billion years old. And the oldest rock, slightly younger on Earth. I think recently people managed to find some rocks in Australia that are about 4.4 billion years old, which is quite cool. But remember, critical thing is, however interesting this is, it is still just a mechanism question. It's not a meaning question. It's not a matter of salvation. We mustn't get it out of context. And it's a minor, not a major. And here is the major, I believe, that the creator and sustainer of the universe died for us. Okay, so I'm done. I wanted to throw it out for questions. I don't know whether any of you've got questions about radiometric dating. Do you sit in the bath and worry about the validity of argon-argon dating? No. Okay. You should. No. Any questions, ladies and gentlemen? Yes.
I've heard of